So if we're going to understand Graham's law, we need a little bit of background, and part of that comes from kinetic theory of gases, because it's talking about gases. And one of the postulates of kinetic theory is that the temperature of a gas is directly related to the kinetic energy of the gas. And of course, kinetic energy is 1/2 the mass of an object, in this case particles of gas, times whatever their velocity is squared. So if the temperature of a gas increases, and it's directly proportional to kinetic energy, it means kinetic energy is increasing. But by simply heating, increasing temperature, you can't change the mass of how much stuff you have. What has to be increasing is the velocity, the speed of the particles. So yes, hot things move faster than cold things on the molecular level. And this understanding is used in Graham's law to compare speeds of two different gases, say hydrogen and oxygen, at the same temperature. Same temp. It doesn't matter what it is. Any temperature. Pick a temperature. Because if I'm going to compare the motion of hydrogen to the motion of oxygen at the same temperature, I know that the two will have the same kinetic energy. However, they have very different masses. The mass of a hydrogen molecule is 2 atomic mass units, whereas that of an oxygen molecule is 16 times bigger, 32 atomic mass units. So for these two guys to have the same kinetic energy, if one of them has a very small mass, it's got to have a proportionally much bigger velocity. So yes, what Graham's law is really saying is that at the same temperature, different gases have different speeds, and it's an inverse relationship, namely the smaller guy, the lesser mass, has to be moving faster, have a greater speed, than the bigger guy. And I always like to use the analogy of football players. The small guys are the ones you see in the speed positions at wide receiver or something. They've got to sprint down the field ahead of everyone else. And the bigger guys don't have to move as fast. They're there on the line blocking. So yeah, I like to think small is faster, big is slower. And that's essentially what Graham's law is. So it's written typically as a proportional relationship, namely that if you know the molar mass of gas A, and you know how big the molar mass is for a different gas, gas B, at the same temperature, their molar masses would be inversely related to their rates of motion. So this would be the rate of gas B, showing an indirect relationship, and this would be the rate of motion for gas A. So yes, we could do a simple problem with this understanding, namely, if methane, and we've identified our gas, methane, so we know exactly what its molar mass is, CH4, would have a molar mass of 16 grams per mole, effuses from a container, the pressure drops at a rate, so we're given a rate of change for the methane, 25 millimeters of mercury per second. That would be a decrease in pressure from the container every second. And the question says, at what rate, so how many millimeters of mercury per second, would a comparable sample of helium effuse from the same container? Now, if it's comparable, it has to have the same temperature. But we have a very different molar mass for helium. It's 4 grams per mole. So intuitively, I know the rate of effusion of the smaller gas will be faster. It's going to be higher than 25 millimeters of mercury per second, because the little guy has to move much faster to have the same kinetic energy as the big guy, who would necessarily be moving slower. And now I just plug some numbers into an equation. And in this case, I'll choose to call the helium gas B, and we'll call the methane gas A. And if that's true, then the square root of the molar mass of methane, that should be 16 grams per mole, over that of helium, 4 grams per mole, should be inversely related to the ratio of the rates. So this should be the unknown rate of the helium, and this should be the known rate of the methane. And we're all set with some simple algebra, because of course if I take 16 and divide by 4 I get 4, and if I take the square root of 4 I get 2, and that has to equal x over 25 millimeters of mercury per second. This should have been per second, of course, it's a rate. And therefore, if I multiply both sides by 25, I get 50 millimeters of mercury per second as the rate of change of the pressure of our smaller gas, helium. And that makes sense to me because helium is smaller, much smaller than methane, so its rate of motion and the rate at which it leaks out of a container should be much faster than that of methane, and it is. And these numbers are easy to see because I know that the helium is 4 times smaller, so it should actually leak the square root of 4 times faster, and that's twice as fast, which 50 millimeters is. So that's one simple example of how we can work problems with Graham's law. Now be careful, because instead of a rate, you might be given an actual time. But that's easily accomplished too using Graham's law, because a rate is a change in some quantity per change in time. So you see, there actually exists an inverse relationship between times and rates. And that should make sense qualitatively, and common sensely, or sense-wise, should also make sense, because if something is moving faster, it should take less time to accomplish something. Again, I think of the big guy and the little guy, the lineman and wide receiver running a race. And of course I know the big guy moves more slowly, that's an inverse relationship, and the little guy moves faster, that's an inverse relationship. But because the little guy moves faster, it will take him less time to run a race. So little guy, little time, that's a direct relationship. So I can also think of Graham's law this way, using times instead of rates. Namely, if I know a ratio of 2 times that it takes gases to effuse, then I know it's going to be directly related to how big they are. So the time for A will be directly related to the size of A, and the time it takes B will be directly related to the size of B. And so in examining this problem, if you have a sample of oxygen, O2, that's 32.0 grams per mole, if it takes it 12 minutes to effuse from a container, and you're asked how long, well, I don't know, that's what I don't know. It will take a comparable sample of carbon dioxide. Well, CO2 is 44.0 grams per mole. I could solve this just as easily because I know the 2 molar masses for oxygen and carbon dioxide. I know one of their times. I should be able to find the other time. It's just I have to make sure that the times and molar masses are directly related. So to do the problem quite simply, I will choose carbon dioxide as gas A, and I don't know how long it will take the carbon dioxide to effuse, but I do know how long it will take the oxygen to effuse. And that should be directly related to the square roots of their 2 molar masses. And the molar mass of the unknown carbon dioxide is 44 grams per mole, and the molar mass of the known oxygen is 32 grams per mole. So these units cancel, and to solve the problem, we divide 44 by 32. We take the square root of the quotient that we get when we make that division, and then we multiply both sides of the equation by 12. And we get the time it takes for the carbon dioxide, the bigger gas, to be a longer 14.1 minutes, which makes perfect sense because after all, it's a bigger gas at the same temperature. It should take longer to do the same effusion from a container because of course the bigger molecule moves slower, therefore it takes a bigger time. Now what we've been doing is using molar masses to find times and rates, but we can do the exact opposite as well. We can use times or rates to find a molar mass, because in this problem we're told that a sample of oxygen takes 8.00 minutes to effuse from a container, and of course oxygen has a molar mass of 32 grams per mole. Then we're told it takes a different gas, but we're not told what the gas is. We have no idea. So we don't know what the molar mass is. But we do know that it takes a time of 6 minutes to effuse. So we have 2 times and 1 molar mass, and this problem asks what is the molar mass of this unknown gas. And all I have to do is make sure I understand my relationship, once again, between size and time. And that's a direct relationship. So I set up a proportion and make it direct. What I don't know is this molar mass for the gas that takes 6 minutes to effuse. That's a direct relationship. I do know it takes 8 minutes for a gas that has 32 grams per mole as a molar mass to effuse. So to solve this equation, very simply, I divide 6 by 8 and get 0.75, and that has to equal the square root of x over 32.0 grams per mole. So to solve for x, I square both sides of my equation to eliminate the radical, and 0.75 squared is 0.563 roughly, and that has to equal x over 32.0 grams per mole. To solve for x, multiply both sides by 32 grams per mole, and when you do so, you get the molar mass of 18 grams per mole for our unknown gas. So this unknown gas in this problem could very well be something like water vapor, because after all, water would have 18 grams per mole as its molar mass. Now the beauty of this is it's one more way that we can disguise a molar mass for a problem in which we always need a molar mass, and that's a problem in which we're asked for a molecular formula. Because after all, for a molecular formula you need 2 things, an empirical formula and a molar mass. So of course, if I'm told that an unknown gas is 30.4% by mass nitrogen and the rest oxygen, then I know in a 100 gram sample there are 30.4 grams of nitrogen atoms and there are 69.6 grams of oxygen atoms. And if I want an empirical formula, I can't use masses empirically because different atoms have different sizes. So instead I need moles. 1 mole of nitrogen atoms would be 14 grams of nitrogen, and 1 mole of oxygen atoms would be 16 grams of oxygen atoms, which means I get 2.17 moles of nitrogen atoms for every 4.35 moles of oxygen atoms in this compound. And immediately I see that what we have is a 2 or a 1 to 2 ratio of these atoms. So I know the empirical formula is NO2, meaning the empirical mass is 14 plus 32, that is 46 atomic mass units. Now to find the molecular formula, I need to know what the molar mass is, the mass of a mole of this substance. And so I'm given in this problem a rate of effusion of an unknown gas and a rate of effusion of a known gas. And so since rates are inversely related to the square root of molar masses, I can say that for my unknown gas that has a rate of effusion of 1.04 unknown molar mass, comparable to 2.50 for a known molar mass of 16 grams per mole for methane. When we do the solving, we get x equal to 92 grams per mole, meaning a molecule of whatever this gas is 92 atomic mass units, and since the empirical mass is 46, half of that, well, we must have dinitrogen tetroxide as a molecular formula.